Okay, for today's lesson we're going to talk about what we call rational functions. And the definition of a rational function is as follows. If f and g are both polynomials and g is not equal to 0, then the function given by f divided by g is what we call a rational function. Okay? Which kind of follows from our definition of a rational number. If I have an integer, like let's say 5, over another integer like 2, okay, we call that a rational number. Any number that can be written as a fraction is a rational number. And so any function that can be written as a polynomial over another polynomial, okay, and of course the g polynomial can't be 0, otherwise we'd have 0 on the bottom, which is not okay. Okay? But if we have something like that, we call that a rational function. Okay? So we're going to study some things about rational functions today, including the graphs, and there's going to be more that we're going to do on Monday next time we meet. But I want to start out with talking about domain issues, because as you can imagine, when we have stuff on the bottom of a fraction, we're going to have domain issues that we need to worry about. And so that's the first thing we want to do, is to find the domain of a rational function like this one. Notice it's a polynomial, 2, okay, over another polynomial, x plus 2. And so we're going to do two things here. We're going to find the domain, and then we're going to use limits to describe the behavior at values that are not in the domain. Okay. So in this particular case, we have 2 over x plus 2. And keeping in mind that what we want to do is figure out that value or values that make the bottom 0. Okay, because those are going to be the values that we do not want as part of our domain. So in this case, of course, if we solve that, we're going to get x equals -2. So that's going to be not in our domain. Therefore, the domain for this problem is going to be -infinity to -2, and then from -2 to infinity. So we'll describe the domain with interval notation as always. Okay? And then ultimately what they want us to do next is describe what's going on at -2 with limits. Okay? So I want you to look at the picture first. If we were to graph this, okay, we would see this at -2. We would have this asymptote here. Okay, so we have that vertical asymptote at -2. Okay? And what we want to do is describe what's going on as we get close to -2 here. So my first limit is going to be the limit as x approaches -2 from the left. Okay, remember, if we want from the left, we put a little minus sign above the -2 right here. Okay, so the question is, what's the limit as x approaches -2 from the left? Well, here's the left over here. We're left of that particular point. And as we approach -2, what's going on with our y values? What are they like? Yeah, they're decreasing and getting how small? This is going to keep getting closer and closer to the asymptote, and it's also going to keep going where? Down. Okay, down to where? -infinity. Okay, so that would be the description of what's going on to the left of the asymptote. And if we wanted to write a limit statement for the right of the asymptote, we'd say -2 with a plus sign. And the answer to that now again is, if we're on the right side of the asymptote, what's happening as we get close to the asymptote? The values are getting what? They're increasing, they're getting bigger, and so therefore the answer on this side would be infinity. Now with every rational function, is it always going to be one of them is going to be infinity, one of them is going to be -infinity? No, not necessarily. Okay, could they both go down or both go up possibly? Sure. Okay, what we need to do is look at the graph though and see, what are they like? Are they both getting infinitely big? Okay, are they both getting infinitely small, or is it one of each? On the left it's getting bigger, smaller, etc. Okay. So this would be what we're going to do to describe the behavior near the asymptote as we were directed. Okay, so that's all about using a limit statement. Okay. Alright, now I want to look at this. This is one of our parent functions. I want to take a little bit of a closer look at this and some of the analysis here that we generally do with all functions. But remember, this was one of our 12 that we looked at, the reciprocal function, 1 over x. This is a rational function. It's got a polynomial divided by a polynomial. Okay. And so in terms of domain here, we know that 0 can't go in here because that would make 0 on the bottom. So our domain would be -infinity to 0, 0 to infinity. If we were to investigate this and look at the horizontal asymptote here, we can see that it's going to get closer to 0 but never actually get to 0 in the y direction also. So the range would look the same. Keep in mind also that if a fraction is going to equal 0, the top has to equal 0, but there's no variable on top, so can it ever equal 0? It always equals 1. It never equals 0, so therefore we should expect that 0 not be part of the range here. Okay. Continuous, this function would be continuous everywhere except for the asymptote, which is at x equals 0, of course. Okay, decreasing, this function is always decreasing on that branch, and it's always decreasing on this branch as well. True. So this function would be never increasing, never constant. Okay, it is an odd function. If we were to put a negative x in here, we'd have negative 1 over x, which would be the opposite. So it's an odd function. We can see by the symmetry here that it's odd. Also, it's symmetric about the origin. Okay. Unbounded, because this goes up forever and this goes down forever. Okay. No local extrema. There's no local maximums or minimums in this function. We do have a horizontal asymptote, of course, as we talked about. We also have a vertical asymptote that we mentioned. Okay. And then, of course, the end behavior. As we go off to the right, what are the y-coordinates like? The y-coordinates get close to 0. As we go off to the left, the y-coordinates get close to 0 also. Okay, one more thing we could add to this if they wanted us to describe the behavior around the asymptote. Okay, we would say that the limit as x approaches 0 from the left would be what? As we approach 0 from the left, from over here, what's going on with these y values? Getting bigger or smaller? Getting smaller, so that answer would be negative infinity. And as we approach from the right, so if we write 0 plus of our function, the answer to that, as we approach from the right, the values are getting bigger, and so therefore we would put infinity for that if we had to describe the behavior around the asymptote. Questions so far? Alright, so the bulk of our work today, though, is going to be dealing with transformations of that reciprocal function. Okay, what happens if we do transformations? If we move that left, right, up, down, have a vertical stretch, horizontal shrink, etc. Okay, how is that going to look? So, first thing that we have here, and these are the directions that you're going to see in your work today, describe how the graph of the function can be attained by transforming this graph, okay, which is the parent graph. Identify the horizontal and vertical asymptotes, and then use limits to describe the corresponding behavior, and then sketch the graph of the function. Okay. So starting with the first one here, this negative 2 over x, okay, you can see that there's two things that are different. Number one, instead of a 1, we have a 2 on top, and then also we have a negative out in front. So based on what our work has been so far, think about what that's going to do for our function. Remember, we started with this as our parent. Okay, if I wanted to get to this, what two things would have had to have been done? Well, I would have had to multiply by 2. Okay, because if I multiplied by 2, that would give me 2 over x. True? And so multiplying by 2, we know creates a vertical stretch. Okay. And then also, we would have multiplied it by negative. Okay, so I'm going to put it like that. And if we multiply it by a negative, then we would get the actual thing that we're looking at. And we know that multiplying by a negative creates a flip over the x-axis. So we have two things here that we need to consider. We have a vertical stretch, and we have a flip over the x-axis. Now, thinking about our original function here, and knowing that it looks like this, and again, it's just a rough drawing here. I'm not plotting points, taking the time to do that. Think about what our new function would look like, and we'll do it with points in a minute, but ultimately, okay, if I do the vertical stretch, it's going to take these and stretch them. It's not going to really change the picture a whole lot in terms of the stretch here with only a multiplier of 2. But that negative is going to make this branch do what? That branch is going to go up here, and then this branch is going to go down here, isn't it? So we should expect that the picture look maybe something like this. True? Alright, and so again, a couple different ways we can do this. We could make an XY chart for this. My suggestion to you, if you're going to draw the graph of a function that is a rational function, that you first of all identify the asymptotes. Okay, keeping in mind that if I were to just have an x on the bottom, I still have x equals 0 as an asymptote. Okay, if I have a negative 2 on top this time, is that going to change the fact that this is never going to hit 0 also in the y direction? No, I'm still going to have y equals 0 as a horizontal asymptote. So I would have my same asymptotes drawn. That's what I would do first. Okay, recognizing that those two things that happen to this function are not going to change the asymptotes. Okay, if I shifted this left, right, up, or down, would that change the asymptotes? Yeah, definitely. So we would want to draw those where. We'll see that in a minute. Okay, and then from there, I'm going to plot some points to get a reasonable graph for this. So one thing that I would always do is recognize that 0 is where we have the asymptote. So I would pick at least 3 points on one side and at least 3 points on the other. Okay, just so I can get a plot that's going to be accurate. Okay, knowing where my asymptotes are. So if I were to put -3 in there, I would get 2/3. If I put a -2 in there, I'd get 1. If I put a 1 in there, I'd get a -1 in there, that is, I'd get a 2. A 1 in there would give me -2, -1, -2/3. Okay. And so if I plotted those points as such, -3, 2/3, -2, 1, -1, 2. Okay, I would in fact get that picture that I expected over there. 1, -2, 2, -1, 2/3. And once again, I know where my asymptotes are. I know I need to go close to the asymptotes. And again, I would do this on graph paper if I were doing it officially, but with that said, I could get a pretty good picture of what that one would look like. Okay, knowing what I know about transformations and being able to draw the graph. Okay. All right, questions so far? All right, let's take a look at another one. This time I have -2 over x plus 3. Okay. Now, based on what I just did with that last one, we already know what the -2 part's going to do. Okay, we already could say that it's -2 times 1 over x plus 3. And we also know that if it's x plus 3, if there's a plus 3 with the x, okay, that's going to create a translation of left 3. Okay. So I want you to think about how I would set up the graph on that one. If I know that it's going to go left 3, it doesn't go up or down at all, so that's not going to change the horizontal asymptote, but it will change the vertical asymptote. Instead of at 0, okay, now my vertical asymptote is going to be at -3. So I would draw that right away. Okay. I would also recognize that it's a 2, so it's going to be a vertical stretch. It's a negative out in front, so it's going to create a flip as well. So the graph we draw shouldn't be too different than what we just did a minute ago, should it? Okay. So what I would do then is I'd make another XY chart. And if -3 is my asymptote, then I would use -4, -5, -6, and -2, -1, and 0. Okay, 3 numbers on each side of the asymptote. Okay. And if I were to plug those in, I would get a -3 in here, and I'd get the same numbers, wouldn't I? Okay. If I were to put those in there, and I get -2, -1, -2/3. Okay. And if I plot again, 1, 2, 3 more this way would get me 2/3, 1, and 2. And then on this side, -2, -1, and 2/3. And this time our graph would again have a similar shape to the previous one that we just did. Okay. The only key difference is that it's slid over 3 to the left because of the x plus 3 on the bottom. Okay, again, questions so far? All right. Now, the last one that I want to look at, we have to do a little bit of work to decide how it's going to look. Okay. And the function this time is going to be k of x equals 2x plus 4 over x plus 3. Now, the key thesis here is that this time, instead of having a transformation of the 1 over x function, either by adding or subtracting to the x, if you will, or putting something on the outside, etc., okay, we have a linear piece on top. Okay, the parent function is not linear on top; it's constant. True. So here's what we're going to have to do for this. We're going to have to actually transform this so that we can see what this is going to look like, okay, in terms of that 1 over x function. So when we have that situation where it's linear over linear, okay, and we want to figure it out based on transformations, what we have to do is we actually have to divide this. Okay, so here's what I'm going to liken it to, though. If we had 7 over 6 in the past, in some classes we were told that that's not okay to leave it like that. True? Okay, and so we would change that improper fraction to a mixed number, and we'd go 1 for the quotient. 6 into 7 goes in there once. The remainder over the divisor would be 1 plus 1/6, and that these two are equivalent. Everybody agree with that? Okay. So if I have that number and that number, they have exactly the same value. True? Well, what I'm going to liken that to is this, where this is like an improper fraction. Okay, and what we're going to do is we're going to change it to a mixed number. So we're going to have x plus 3, 2x plus 4, and we're going to actually do the division just like we did over here. It's no different. Okay, it's a little harder because we have to do polynomials instead of numbers, but if we do x into 2x, that's 2, and I'd have 2x plus 6, that is. Okay. I would parenthesis and subtract, and I'd get 4 minus 6 would be negative 2. And I'd be done with the division at that point because we have our remainder with a degree less than the divisor. So as an improper fraction, it's this. As a mixed number, if you will, it's going to be x plus 3, and then minus 2 over x plus 3. Oops, I lied. Quotient, sorry. It's going to be 2 minus 2 over x plus 3. Alright. Now, looking at it in that format, again, if that works here, if these two have the same value, and if I do that exact same process with this, okay, this being like the improper fraction version, this being like the mixed number version, okay, if these two have the same value, then these two should have exactly the same behavior, shouldn't they? Okay, because these aren't two different functions, these are the same function, we just put it in a different form. Fair enough? Okay. Now, if you look at it this way, instead of writing it as 2 minus 2 over x plus 3, if we write it as negative 2 over x plus 3 plus 2, okay, didn't we just graph this a minute ago? And then what is this going to do to the whole thing? It's going to move it up 2, isn't it? So if you look at the graph that we just drew, which is right here above, okay, wouldn't it be exactly the same graph, but ultimately just moved up 2? Okay. So when I draw that, I'm going to draw the asymptotes in at negative 3 again for the vertical one. Okay. And this time, instead of having 0 as an asymptote in the horizontal direction, I'm going to have 2 as a horizontal asymptote, aren't I? Okay. And then from there, can I plot some points and draw the graph just like I drew the rest of them? Okay. And that's exactly what we do. It's going to look exactly the same.